Hi, it's time for another math easy solution. Turn scores further into calculus with parametric curves, and now look back at the area series, which I went over example 1. That was, I believe, a few months back. And now look at example 2 of it, which is a continuation of my last video on just parametric curves, example 1. So yeah, the numbering of this is a bit messed up. But anyways, what I'm going to do is I'm going to build up from my last video and now look at the cow tied to a silo problem, or basically the grazing area, and I'll get to that in a bit. And I'll do method 1, which involves parametric equations, and in the next video I'll show you that it's actually simpler without parametric equations, just to show you the difference. So here's example. Example states a cow, I don't know why this is capitalized, a cow is tied to a silo with radius r by a rope just long enough to reach the opposite side of the silo. So you have, here is a cow tied to the silo. It's the radius is r, like that, and it's tied to it, and it's just long enough to reach this point right there. And now we're asked, find the area available by the cow for grazing. So as you can see, if it goes all the way around, the silo gets to this point, and then if it tries to wrap around while this is held taut or tight, this is the correct way of calling it. So tight, then what you get is you get a shape like that. It rolls all the way around. So let's go ahead and start solving this. Yeah, so let's look at the solution. So first, recall from my last video, which was on parametric calculus, example 1 on the involute curve, and this curve is called that involute right there, involute, or involute, like that. And basically in that video I went over the involute of a circle and the resulting parametric equations of the involute curve. Yeah, so I'll write those parametric equations soon. So basically what we end up having is, if we want to calculate this area, let's say we have x, y, just to show you those curves first, we have the center. And I'll draw the center, the silo, in red. So we have like that, there's the radius r, this is the angle theta. And then what we end up having is, when this goes all the way to pi like that, the straight line across here goes all the way up this high like that, and it's vertical. Let's draw this a bit more vertical like that. And at this point, when you hold it tight, it just becomes like a tangent line where this is right angle across. And now I'm just going to draw this in black, the curve. The resulting curve looks something like that, and this is the resulting curve. That's y. I'll just put that fix up that vertical axis. So we have a curve like this, and these coordinates right here, x, y, as I showed in my earlier video, yeah, they were actually, before I get to that, I'm going to look at the flip side of this. So if you look at the flip side, it's just a mirror image, because that rope can go all at the bottom as well. Let's draw this, trying to match the scale. So go something like this. Yeah, so that's on the bottom side, matching this area across there. But then this other side, it doesn't involve the involute. That is, well, just graphing it across like that. It's actually half of a circle. Yeah, so I'll just draw that separately like that. And where x, like I showed in my earlier video, is equal to r cosine theta in parametric form, plus theta sine theta, and y is equal to, if I remember correctly, yeah, it's sine theta minus theta cosine theta. So yeah, that's now that we have written these, and again, make sure to watch my last video to get these parametric equations, how I got those. So basically, I also want to point out again, as I just stated, the involute curve only accounts for the area enclosed as the rope is quote, unwinding from the circular silo, but then once over here on the left side, it's free to move around anywhere on the left side. Thus we can break down our total grazing area as follows. And what we'll do is, let's just draw our silo. So silo is in the center like that. I'll draw it actually like that. Now from here to here, this length across like that, that's the length of the rope. That is in fact pi r, because, well, that's just half of the circumference. Remember, this angle across, that's just pi. I'll draw this dashed line across like that. And again, you could recall definition of radian, and again the pi is in radians. So if you recall definition of radians, and basically it involves the length of the circular arc like that, where this is theta, this is r, this a equals to is defined as r theta, and that's in radians. That is the definition. Let's just put this in a little bubble. Yeah, so now that we have that, let's just graph the involute. The involute goes something like that, and it cuts off right over here. I'm just going to draw this like this. Yeah, then the bottom part here is going to be something like this. Let's draw this a bit better. One more. Try this again. It looks something like that. So what I'm going to do is I'm going to call this area across here A2. Oh, the other one I'll show you after. And this one's identical. This is also A2. So we have two of these areas above. And then the other part, when this line is fully straight, that's the length of the half the circumference. I just fix up the circle, make it look nicer. That's pi r. So then when it's fully straight across here, and I just fix that up as well. This is going to be pi r. This is also going to be pi r, the length of the rope up to here. And in fact, when you straighten it out all the way across here, you also get pi r. So then we get a half of a circle. I'm going to just fix that up, and then I'll draw this length right here. That's just pi r, the radius. So now we have half a circle like this. I'll draw lines across like that. Now this is just, I'll call this A1. Yeah, I'll just put A1 inside here. And so that's our A1, and this is just half of a circle. Yeah, so thus what we have is thus total area. I'll just write this as A equals to the summation of the areas. That just equals to now A1 plus A2, 2 times A2. So 2 times A2 like that. Yeah, there is what our basic formula is, and now we can solve A1 pretty easily. A1, this just equals to half, this is going to be half the circle area, so 1/2 of pi radius of that circle squared, which equals to, that's just pi r. So yeah, that's just pi r across, and bottom and everywhere it's just pi r. So we have 1/2 pi r, and then squared, and then what we end up having is, well, 1/2 pi times pi squared r squared, and then we have a pi cubed. So A1 equals to 1/2 pi cubed r squared. Alright, so now that we have that, let's start solving this part, or the area A2 part. So the A2 one is more complicated. So for area 2, put a circle around this. Yeah, what we first need to do is let's just draw our silo, or a circular silo. I'll put that in red, and I'll draw the axis dissecting through this like that. There's x, there's a y, and now let's just draw our curve, or our involute. Involute's going to look something like this, and then only up to this part here. Just deal with that. Actually, I just erased that involute because we need to make sure of some things right here. That is, the rightmost point is at when this angle is pi over 2, so that we have an absolute straight rope across. So that's obviously going to be the rightmost one, so it connects all the way across like that. And then this flat one is when we have across here. Yeah, across here is at pi, so that's angle 180 degrees, and this is a vertical line, again a straight line at this point, and this one is at over there, and we get this point, and then what we get is, then we just keep drawing this involute, and we get something that looks like that. Let's just fix this up, and yeah, just quickly fix that up to make it look nicer. And so at this point right here, we'll just deal with the parameter theta. This is when theta equals pi over 2, and then we get our xy coordinates there, and then here is when theta equals to pi, equals to pi like that. And at this point right here, this is when the theta is just equal to 0. So it's just a flat line across like that. Yeah, so now that we have set this up, now to solve Yeah, the area of this top part, what we're going to have to do is, well, we could use basic integrals to solve area and by using infinite amount of rectangles. For example, if we were to look at a section here, infinitely small rectangle, there's a height y and it's a width dx like that. The problem is once we get to this point here, and then when we do that, we're summing, well, empty space. So what we have is something like this. This is y, and now we have this is dx like that. But then this section we're going to be summing up from in between 0, theta equals 0 to theta equals to pi over 2. This as well can be seen as, quote, empty space. So empty space like that. So we need to subtract that as well as this the top part of this circular silo, because that includes this part right here that's added. So thus what we end up having is, thus area 2 is going to be equal to, I'll draw this visually to show you what it means. So we'll have this part right here, and then all the way to pi over 2. This is that's at pi equals, that's at theta equals to pi. And then at this point, then we have a vertical line down, and this is going to be, this is just integral from pi or theta equals to pi up to pi over 2, and this is y dx. So that's this summation from here to here, and I'll put this point like that. This is at theta equals to pi, this is theta equals to pi over 2, like that. And then, but then we need to subtract this part right here, and we could put a minus sign, and then what we'll have is right here is going to be this section like that, where this summation or this integral is going to be from, well, this is theta equals to 0, and this is up to here, again that's our theta equals to pi over 2, and this is just integral from we're going to go from left to right, so 0 or theta equals 0 up to pi over 2 of y dx. That's same formula. So we're using theta as the parameter, so we're going to use substitution later. And then we also need to subtract the silo, or the top part of the silo like that. So subtract it by this part right here, where there's just a half circle, radius is r, and this is just pi r squared, area of a circle, divided by 2. Yeah, so thus what we have, we just write these down, we have area, or a2 equals to the integral, this part from the integral from theta equals to pi up to pi over 2 of y dx, subtracted by, now we have the integral from theta equals to 0 up to pi over 2, like that, y dx, and then we have to subtract by this half circle, so pi r squared over 2. Yeah, so notice what we have though. We have this angle goes from pi to pi over 2, and then it's from 0 to pi over 2, but then what we could do is apply integral property, so we can get this is pi over 2 dx. So instead of adding, we could instead of subtracting, we can add and then flip these upside down, so we get from equals to, so we get a negative 1 right here, so this is from pi over 2 to 0 of y dx, and this is, and then we again subtract pi r squared. So notice what we have right here. We go from pi to pi over 2, and then there's pi over 2 to 0, so we can just combine these together. So combine, because the endpoints, this one is the same as this one, so we circle that, circle that. So what we have is area 2 equals to the integral from theta equals to pi up to 0 of y dx minus pi r squared over 2. So notice what we have now. So we have this, but notice this is actually an amazing result, because now this means we can go from theta equals to pi all the way to here, and it will automatically subtract the empty space, because when you go from here to here, it flips and makes it negative. So that's absolutely amazing. Yeah, so I'll put that right here. So this is an amazing result. This means that simply taking the integral from theta equals to pi to theta equals 0, we automatically subtract the excess area due to the function not being a one-to-one. Yeah, not being a one-to-one function. That's this part right here. It's not one-to-one because, well, I'll just draw that right here just for a reference. If you have x, this is y. If you have a curve like this, for example, and then if you have at x, right here, I'll call this x1. At this point, we're going to have, well, y1 and y2. So we have, so what we have is here 2 y's for 1 x. In other words, not 1 to 1. Yeah, just for reference. For these kind of equations like that, but what I just showed that it is, for this case at least, it still subtracts it, which is quite amazing. Now I may investigate this further, develop a more general case, so hashtag stay tuned to see how it works for other cases. But for this one is pretty cool like that. So let's just go back to solving this. Now that we have that formula, let's solve this one first. This from integral from from theta equals pi to 0, and just ignore that part right there. So we have thus, and then you apply substitution rule. This is pi or theta equals to pi up to 0 of y dx. Then what we need to do is again apply substitution rule to get the parametric equations. Apply substitution. Okay, and then what we get is well, first of all, recall that y equals 2, and well, let's just scroll up again. This is from my last video. Y equals r sine theta minus theta cosine theta. Then x is the cosine theta plus sine theta. Yeah, so jumping here, we have r sine theta, and there's a minus theta cosine theta, and then the x, because we need to, there's our y, then we need to get the dx, so x equals to r cosine theta, then plus theta, then we switch to a sine theta, like that. Then take the derivative dx over d theta, this just equals to, well, r inside here is negative sine theta, plus, and now we need to apply the product rule here, so derivative of theta, that is just, well, that is just 1, so then 1 times sine theta, plus now we take the derivative of this one, so we just write theta, and then derivative of sine, that's just cosine theta. Notice here, negative sine and positive sine cancel, so, and then move the d theta on the other side, so we get dx equals to r theta cosine theta d theta, like that. So we could throw that in there, and I'll just circle this one like that. So plug that in, or before plugging it in, what I'm going to do is, well, I'll circle this part is the ones we need. I'm just going to write y and dx and try to simplify it. So thus we have y dx equals to r sine theta minus theta cosine theta, and then this part right here, which is r theta cosine theta d theta. Yeah, like this. Now if you multiply that out, what we get is r, and then we have an r squared here, the theta goes into there, so we have theta cosine theta cosine theta, and then we have a minus, then a theta, so we just took the r out of both of them, and then the theta times by theta there, we have theta squared, and then cosine squared, like that, and then take the d theta out, just leave it out on the outside, like that, so d theta. Yeah, so now we could simplify this even further by looking at this sine cosine right there. So first of all, recall. So we're going to look at this one simplified. Recall the trig identity, or the double angle trig identity, that I derived in my earlier video. Put that in a link below. Basically, sine 2 theta equals 2 sine theta cosine theta, like that. Then we can, well, divide this 2 out, move this over, so I'll just do this, divide by 2, like that, equals that. So then this part equals to this, that's just this part, and then we could replace it, So thus we have y dx equals to r squared theta sine 2 theta over 2 minus theta squared cosine squared theta and then d theta. Yeah, so thus our resulting integral is going to be the integral from theta equals to pi up to 0 of y dx. This one is just equal to, now replace the y dx with that. That's just going to be, now we could just write pi because we're going to be dealing with this parameter. We don't need to write theta equals to signal as a different parameter than this x or y. So we have this from pi to 0 of r squared, and then we have this giant theta sine 2 theta over 2 minus theta squared cosine squared theta, like that, and then d theta. So yeah, this is the integral. Let's just circle this. So yeah, this is very tedious just to get to this integral, but it's actually even more tedious to solve it. So yeah, this integral is very tedious to solve. So I've just calculated with an online integral calculator. I may go over this integral manually in a later video, so stay tuned, or hashtag stay tuned for that video. But yeah, for now I'll just use the integral calculator, otherwise the video will take forever. So we have this. So this website's pretty amazing, integral calculator, integral-calculator.com, and we get this result. I just put x instead of theta. So let's just double check it's the exact same. So we have x, sine 2x over 2. This is theta sine 2 theta over 2. Then minus theta squared cosine squared theta, or x squared cosine x squared. So we get the resulting one, something like this, but it simplifies it over to here. This is a giant one like that. Yeah, so what we have is that's the resulting one. There's a constant c at the end. So thus, I'll just leave this arrow, I'll remove the arrow. So thus we have integral from pi to 0, or theta equals to pi 0 of y dx equals to this entire thing. Yeah, this entire thing, what I'm going to do is I'm going to take out the constants, which are, well, the r squared and the negatives, as well as the 12, so that we have r squared, or negative r squared over 12, and then this is going to be, we could remove that c, this is just going to be 3 theta, replace x in this case is just equal to theta. Yeah, like that. So just the x just replace with theta for this case, it's just the same thing. Just because it's easier to type. And I'm not sure if theta works for that calculator. But anyway, so we have this. This is 3 theta squared minus 3. Then we have a sine 2 theta plus 6 theta cosine 2x, or 2 theta plus 2 theta cubed. Yeah, cubed. And this is all integrating it from, this is from pi to 0, like that. So let's just evaluate this. So to evaluate it, we plug in the 0 first. So we get this negative r squared over 12. And now what we get is, well, this is just 0. Sine of, this one was 0. We have negative 3. Sine of 0 is just 0, and I'll show that in a bit. Actually, I'll write that here first. So recall. So if we have sine, let's just go with theta, and this one here is angle like that. This is sine theta, and this is at 0. That's just 0. So as you can see, that goes to 0. So we have that. So we just have 0, and then there's a 0 there. There's a 0 there. So that's everything 0. So 0, subtract this by. Now we add the pi's in. 3 pi squared minus pi, or minus 3, not pi, sine 2 pi, just to put a big giant bracket like that because we're subtracting the whole thing, plus, now we have 6 pi, and then cosine 2 pi plus 2 pi cubed, like that, and there is what we have. And now notice here, the sine 2 pi, that's also 0. So that goes to 0. Now for the cosine, we know that I'll put the y like that. Cosine looks something like this. I'll draw this better. So the cosine looks something like that. Where at this, remove this 0, this is at 2 pi. This is our cosine function. And as you can see, this one is at 1. That's a 1 height. So this means this value goes to 1. So all we're left with is 6 pi plus 2 pi cubed, but we're subtracting it, but then there's a negative here, so let's just add a positive like that. So drag this in. What we end up having is our integral from theta equals to pi to 0 of y dx equals to, well, now that's a r squared, everything's positive now, r squared over 12, and then we have, this is just going to 0 like that. Now we're left with 6 pi plus 2 pi cubed. So yeah, right here, whoops. Yeah, like that. 6 pi plus 2 pi cubed like that. Let's just double check. Yeah, 6 pi plus 2 pi cubed, everything else goes to 0. So now let's just divide this inside. This equals to r squared, just divide the 12 inside. We get 6 over 12 like that. 6 over 12 pi plus 2 over pi cubed. I mean, 2 over 12 pi cubed like that. This cancels. We're just left with now, we're left with this integral from theta equals to pi to 0 of y dx. This equals to r squared. This is pi over 2, and that's just going to be, well, that's 1, 2, this is 1, this is 6. So we have now pi cubed over 6 like that. So there is our integral, the value of it like that. So now the next step is to finally solve what area 2 is, or a2. So what this is this giant integral minus pi r squared over 2, or half of the silo, the circular silo's area. So thus what we have is, let's go back here. So we have, right here. So thus, I'll put an arrow like that. Area 2 equals to, remember this is equals to theta equals to pi up to 0 y dx. Subtract this by pi r squared over 2, which equals to r squared, pi over 2 plus pi over 6 like that. This is pi cubed over 6. And then we're subtracting this pi r squared over 2, that's the half of the area of the silo like that. And now this equals to, let's just factor out the r squared. So factor it out, we get now a pi over 2 plus a pi cubed over 6, and then subtract this by pi over 2. This just cancels. So we're left with finally pi cubed r squared over 6. So that is our area 2 like that. And now finally, let's just add these all up into the giant formula for area. So remember, the area is the summation, or the total grazing area is equal to A1 plus 2 A2 to get all this, because we have 2 of these A2s. So, and where A1 is just half of that circle, half of that circle with radius pi r. So that's 1/2 pi cubed r squared. So finally, let's just scroll down. This is extremely tedious, but now finally we're back. So we have area, total area is equal to the summation AI. This is going to be A1 plus 2 A2, where that's A2, and A1 is equal to, this was just our pi cubed r squared over 2, because we have, the radius was pi r, and half the circle pi r squared. So we have this minus, this is plus 2 times there. This is going to be pi cubed r squared over 6. Now instead of dividing this, notice we have pi cubed r squared, pi cubed r squared. And now this one, common denominator of this would be 6 if we just multiplied this part by 3 over 3, so that we end up having a pi, or 3 pi r, pi cubed r squared over 6, plus now we have a, just leave that in, over 6 like that. This just adds up, is the same common denominator like that. I'll just move this over, and these are the same, so we could just add those up. So this equals 2, so area equals to 5 pi cubed r squared. Yeah, 5 pi cubed r squared over 6, like that. And there's our area. Yeah, so this is our total grazing area for the cow, and it took all that and all that work and finally get this nice neat little equation for it. So all we need is the radius, and then we get the total grazing area. So it's pretty cool. So yeah, in my next video, yeah, I'll go over a much simpler method to solve for the grazing area, and which doesn't involve parametric equations, which greatly simplifies it in this case. So hashtag stay tuned. It's gonna be quite amazing to see the difference. Anyway, that's all for today. If you followed along, it's extremely tedious and it's and I didn't even finish the whole thing. I guess this integral itself is extremely tedious, so I might do that separately in another video. Just use a calculator to save time. But yeah, this is an extremely tedious video, but hopefully you followed along to see how to solve it using this method, and I'll show you the next and the easier method using the area of a sector of a circle, which is quite interesting. Anyways, that's all for today. Thanks for watching, and yeah, like always, you can download these exact notes, the link below, as well as on Steemit. I'll be uploading it there shortly after I upload this video. Anyways, thanks for watching, and stay tuned for another math easy solution.